Professor Solanki has given us a good introduction. The Sun is currently doing something which we haven't seen it do before. My job is to talk about the extent to which historical records will tell us whether it has done it before, how often, and what we might learn to expect. Where's the... Oh, thank you.
I'll change it for you.
Okay, the outline of the paper is before you. It will be based on the paleocosmic ray record, which is based on a number of cosmogenic nuclides. I will explain that a little bit because in the last 10 years, the whole story of the cosmogenic nuclides has changed very greatly. And I want you to just understand where we are now in that. I will look at the last 1100 years to get a feel for what we might expect. I'll use 10,000 years to get statistics, and then we'll talk about a few other issues. Next, please. Very briefly, the data is obtained from a process which happened back in the past when a cosmic ray whacked into the top of the atmosphere. It produced a cascade of protons and neutrons. These interacted with oxygen and nitrogen and argon atoms. Spallation processes then were archived in ice. There was a parallel path through carbon-14, which I will mention briefly a little later. There's another process entirely whereby very intense cosmic radiation from solar flares can produce nitrates in the polar atmosphere, which are also sequestered in ice cores. And that gives us a method of looking at the paleocosmic ray solar flare occurrence. Next, please. Let me just explain where we have come from in the last 10 years in respect of the paleocosmic ray data. 10 years ago, we knew that there were variations in the carbon-14 and the beryllium-10, but we couldn't relate them to our experimental measurements with neutron monitors or with satellites. In that 10 years, we've come forward in a number of directions. First of all, the satellite measurements have given us a much better understanding of the manner in which the solar activity changes the spectrum of the cosmic rays. We have used very large mathematical models to simulate the nucleonic cascade in the atmosphere, which produces protons and neutrons, and then have used nuclear cross-sections to estimate the manner in which production of the cosmogenic nuclides depends on energy. In other words, we are developing the relationship between incoming flux and the production of the nuclides. There's one major issue still remaining, which is then how those nuclides, which are produced both in the stratosphere and the troposphere, are sequestered in ice. Large global circulation models in the last several years have answered those questions. So we now can quite accurately intercalibrate the paleocosmic ray records with the modern era, and that's what I will be doing now. Next, please. But just to give you an idea of what this is telling us, there we have the relative response of the neutron monitors, which are well known, which you can see have peak energy response at about 5 GeV. The beryllium-10 that I will be using in a moment has a peak response in the vicinity of 1 GeV, sort of midway between the neutron monitors and the higher energy spacecraft measurements on IMP and such spacecraft. So we can see now how the beryllium-10 and the carbon-14 are more sensitive to long and short-term changes than neutron monitors. More important, we have the interconversion calibrations, which I now use. Next, please. Just very quickly, of course, to define the terms which you all probably know, the solar grand minima are occurrences such as occurred during the Maunder minima, 1650 to 1715, the Dalton and the Gleisberg minimum of 1900. Next, please. So now let's look at what the paleocosmic rays were doing during those minima. We're going to look primarily at the minima. And look at the one for the Maunder minimum. You can see that the cosmic ray flux, look at the South Pole in the middle there. I better have the, where's the pointer? Oh, great, thanks, yes. Yeah, sorry. Okay, looking at the middle panel here, that from the South Pole you can see that on the far right, the current intensity is about half of what it was during the Maunder minimum. We can see that during the Dalton and the Maunder and also 1900, the intensity was considerably higher. That is, the amount of beryllium-10 or the cosmic rays were considerably higher. And you can see there were similar events earlier called the Wolf and the Oort minima, which we know were periods of low solar activity because there were low aurora recorded in the old history records of Europe. Now, those data are averaged over 22 years, so they've averaged over the 11-year cycle. Let's have the next one, please, Joe. Here we now have the paleocosmic ray data for the last 600 years, where we can see the 11-year variation. You can see there is substantial variation through the whole period. You can see yet again that the intensity was high during the Maunder and so on. The question I want to look at now is, to what extent was the Sun still varying the cosmic radiation flux during the big minima? That is, was there still a varying magnetic field? Was there still varying modulation? Next slide, please. Now, this is the Spira minimum, which is the most profound minimum we've had in the last 1,000 years. It lasted about 100 years, 120, and you can see that the modulation, the variation, continued through that whole period. It was a quite substantial variation. We, in the cosmic ray community, have something called a modulation potential, which is not a very good measurement, but it's a parameter anyhow that gives you something. And it was a roughly 200 MeV modulation function change. This was a substantial variation. It tells us that the magnetic fields were varying substantially, certainly on a 22-year periodicity, but the 11-year was there as well. Next slide, please. So now we know that the cosmic ray intensity was high during periods of low solar activity. We have seen 5 of them in the last 1,000 years. Let's now look at the last 10,000 years. Here we have at the top the beryllium-10 production record, at the bottom the carbon-14. There are differences. There's an important issue here that the manner in which they are stored, one in ice and the other in trees, are quite different, and the noise terms in each are different from each other. So by combining them, getting the production signal out of them, we can get rid of most of the noise, and that's what we do now. I do point out that the glaciologists put time the wrong way for us, and so note here that it is time before present. A long time ago was on the right, now is on the left. And just to remind you of that, I have time on the time arrow henceforth. So combining these data, next slide please, this is then the 10,000 year cosmic ray record. There's the Spira minimum. The core did not have the Maunder in it. It didn't start till it was down about 1500 AD. The most important thing to notice, I think, is that there are about 22 Maunder minimum or Spira minimum type events. That is, the Sun does this frequently. And these are the big ones. There are smaller ones down in this grass here. The red line is at the present situation, and just for reference, these low values through here are because the geomagnetic moment was about 20% higher then than now. So that's showing us both what the cosmic rays were doing, but just as a check, you can see what the geomagnetic field was doing. Next, please. Now I'm going to change quickly to, very briefly, the question of solar energetic particle events. The paleocosmic ray record does include such signals. The largest one known is the Carrington event up at the top. During the Gleisberg cycle, the Gleisberg minimum, that's one of the low grand minima, it's not quite a grand minima, but around about 1900, there is a burst of very large solar energetic particle events. Some, including a couple that are not on there, there were some 8 large events. One of them, the second largest in the whole record, and so here we have very substantial production by the Sun. If we go back to the Dalton minimum, we find just the same bunching of production of solar energetic particles. And there are theories about this. I won't go into it now because my time's running out, so we'll move on to the next one. Using Parker's transport equation, we can make approximations, I stress approximations, as to what the magnetic field at the orbit Earth was doing. And here's the estimate for the last 600 years, a steadily ramping up intensity with 11-year modulation on top of it, going up to the 5.2 at solar minimum that we've observed until recently, and of course it's now down to where the second arrow is. So this would suggest that the magnetic field is beginning to reverse downwards. Next, please. If we look at the last 10,000 years, this is an estimate by Friedenstein-Helber for that period. Note time is going the right way this time. We can see the grand minima. The one I want to point to is the bottom curve, which is showing us that there's a long-term variation of period 2,200 years. This was detected by Chuck Sonnet 30 years ago. But this is the first time we've ever known what its phase is. You can see here that it was a minimum, and in fact it is defined by the bunches of grand minima that occur. And so the Maunder minimum, the Spira minimum, cause that low value there. This tells us that that cycle is probably a quarter of its way through to the next minimum in 2,000 years' time, which is suggesting, as I'll show in a minute, that we certainly are not going to have another Maunder minimum. Next slide, please. So let us summarise what our historic record has told us as to what's happening now. First of all, it suggests to us that reductions in solar activity, such as are occurring in this minimum, have occurred quite frequently in the past. Very large reductions, such as the Maunder or Spira minimum, roughly once every 500 years, but a bit clumped. The smaller ones, once every 100. And so on. You can see that the cosmic radiation fluxes are high. The durations of these events are 1 to 5 solar cycles and so on. And I won't dwell on that anymore because to allow some time. But finally, and I stress that the next slide should not, my authors should not be blamed for the next slide. This is me and me only saying, if I look at the data, if I look at the paleocosmic ray records, what do I say is about to happen? So there's the prediction through looking at the paleocosmic ray record. A Maunder minimum is most unlikely because of the Halstead periodicity that I mentioned. The Dalton minimum is my bet because what I didn't point out was that there's a periodicity in the records. There's a very clear and quite fixed 208-year periodicity at the de Vries cycle. And this, to me, we're just about 208 years from the Dalton. The event like 1900 is possible, and a non-event is, by my counting, not likely. Thank you. Next one. And that is thank you. Professor Solanki has given us a good introduction. The cosmogenic nuclides has changed very greatly, and I want you to just understand where we are now in that. I will look at the last 1100 years to get a feel for what we might expect. I'll use 10,000 years to get statistics, and then we'll talk about a few other issues. Next, please. Very briefly, the data is obtained from a process which happened back in the past when a cosmic ray whacked into the top of the atmosphere. It produced a cascade of protons and neutrons. These interacted with oxygen and nitrogen and argon. The Sun is currently doing something which we haven't seen it do before. My job is to talk about the extent to which historical records will tell us whether it has done it before, how often, and what we might learn to expect. Where's the... Oh, thank you.
I'll change it for you.
Okay, the outline of the paper is before you. It will be based on the paleocosmic ray record, which is based on a number of cosmogenic nuclides. I will explain that a little bit because in the last 10 years, the whole story of the